This is the beginning of chapter 3. I think it's the first half. So actually, we're not going to go over quantum numbers to the next PowerPoint. So one thing you may not know about light is that all light, every single source of light, whether it be from a light bulb or the sun or a match, or a flash of light from a lightning bug, any source of light is the result of an excited electron in an atom that once it's excited, it drops back down to a lower energy level, and that excess energy is given off as light. So I remember I thought that was fascinating when I learned that. A spectacular display of that is Aurora Borealis, the northern lights. I don't know if any of you are fortunate enough to have seen that, but that's on my bucket list. So how on earth does light come from an atom? Well, this is actually the Bohrs model of an atom, if you've ever heard of that. So it's after the subatomic particles were discovered and after the nucleus was discovered. Bohr's primary contribution was that electrons, my dog just bumped into me, sorry. Electrons exist only in certain energy levels, that they can't just contain a certain amount of energy, that they have to be in specific energy levels. And so we say that electrons are quantized, okay? So this is a picture of Bohr's model, and you can see in the middle in green, that's the nucleus. And then each of the rings represents an energy level that electrons can exist in around the atom. And as you get farther away from the nucleus, the energy increases the farther you are away. So just to kind of see a visual of what we said on the last slide. So if you give an atom energy, and it can be energy in the form of light, it can even be mechanical energy or heat, but if you give it enough energy for an electron to be excited to a higher energy level, then that's an unstable state, right? Everything likes to be in the lowest energy state. And so very rapidly, that excited electron will drop back down to a lower energy level. And in the process, it will emit light. And so depending on it can be all different wavelengths of light, and the wavelength or the energy of the light depends on the spacing between the energy levels in the atom. So there are quite a few different electronic transitions that can happen when you excite an electron. So let's say that you have an electron in the lowest energy level, we call it n equals 1, and let's say that you excite it up to n equals 6, the 6th energy level. Now that electron may drop all the way back down in a single transition to its ground state energy level, or it may pause and drop partially down. So it could just drop from the 6th energy level to the 2nd, or the 6th energy level to the 3rd. And so we're not going to go over the specifics of these, but just so that you know, there are a lot of different emissions of light you can get from one particular atom. So here's an image of the Bohr model again. And as I said, the distance between the energy levels in the electronic transition determines the type of light that's emitted. So if you have a large energy gap, you're going to have more energetic light. And if you have a smaller change in energy, okay, like energy level 2 to 1, you are going to have a less energetic light that's going to be released. And I don't know if you remember Roy Biv, but Violet light, as far as the visible light, violet light is the highest energy, red light is the lowest energy, and so that kind of corresponds. And you may have done an experiment in high school chemistry, if you took it, where you sampled different compounds in a Bunsen burner. And you found that when you did that, different compounds emitted different colors of light. And that's what this is all about, right? So the primary electronic transition that electrons undergo in sodium emits a yellow-orange type of light. And potassium, on the other hand, when it's excited, the primary transition for the electrons emits a violet light. And so elements can actually be identified by the color of light they emit. And that's one of the ways that we determine the composition of distant stars is by the colors of light they emit. There's something called an atomic emission spectrum. So we have equipment for this, right? We don't just stand and put it in the Bunsen burner. And so an atomic emission spectrum of a particular element has several transitions. Wherever you see a line of light represents an electronic transition of an excited electron. And as I said before, there are several, because you can get excited to the top energy level and then drop to all different lower levels. And so each element has its own characteristic atomic emission spectrum. And we can identify quantitatively the elements that are present in a substance by doing atomic emission spectra. All right, so there's a way to calculate the energy between various levels in an atom also, and it's called the Rydberg Equation, named after the person who proposed it. So what it does is it relates the wavelength of light emitted, 1 over the wavelength, right? And RH is Rydberg constant. And by the way, I always give you constants on your exams. I don't expect you to memorize them, but you may want to jot this formula and constant down to have it handy, because you will have practice problems with it. And it looks like I forgot to identify what N is. So N is the energy level in the atom that the electron starts in and ends in. There are actually a couple of versions of the Rydberg equation, and again, I will give you these equations on an exam. But there's one in terms of wavelength here, and then there's one in terms of energy. And they're similar, but a couple things I want to point out is that there are two Rydberg constants. There is one if you work at the equation, if you're looking for wavelength, and there is a different one if you're looking for the change in energy. Also, the change in energy has a negative sign in front of it. Now, there are actually different versions even than these two that get rid of this negative sign and switch the N values around. So all of them work, okay? So you can use mine. If you have another source that gives you another one, you can use that. Just be very careful of all the different variations. And I'm going to work a sample problem for you. So this problem is asking for the change in energy, but I'm going to expand it to change in energy and wavelength. So I'm going to show you using both of those equations. Okie doke. So let's see. Here, I'm going to do wavelength first. So here's the equation we want to use for wavelength. And here's the Rydberg constant. And remember, it's the final energy level, which is energy level 2, minus, why is my pen acting funny? Minus the initial energy level. Be careful with this section. This is where silly mistakes are made. So You might want to, like I said, run through this in your own calculator and just kind of get used to doing this type of calculation. 1 divided by 2 squared, which is 4, obviously, is 0.25. 1 divided by 9 is 0.11. And so when you work that out, the wavelength transition, it's 0.14. Multiply it by the Rydberg constant, and you get this massive number. Now, very, very, very important. If you're spacing out, listen to me. This equation gives you 1 over the wavelength. That is not a useful number. You need the wavelength, so you need to flip this whole equation upside down. In other words, wavelength is going to equal 1 over whatever you get here. And so what you get then for the wavelength, remember the symbol for wavelength is lambda, you get that it equals 6.51 times 10 to the minus 7 meters. This equation gives you, wavelength is a distance, so it's going to come out of this equation with units of meters. Now, there are several problems that are going to ask you for the wavelength in nanometers. So you need to remember the conversion factor between meters and nanometers. Okay, there's 1 times 10 to the minus 9 nanometers in 1 meter. Nanometers are teeny tiny little specks. So when you do that, you get 651 nanometers. Okay, so now I'm going to go ahead on the next page and work out the Rydberg equation for energy. So if you can find enough energy yourself to work out the equation yourself, I think it'd be good. These equations, the idea is to work enough practice problems that it becomes almost muscle memory for you, because under the time constraints of a test, you really don't want to have to pause and think that much. And here is calculation for the energy of that particular transition. So here is the equation we're going to use for the energy transition. Remember the negative sign, okay, and it's final minus initial, just like the other one. So we already know from calculating wavelength what this value is, and it's 0.14, so that's a little bit easier. So I just multiplied 0.14 times this other Rydberg constant, and I get that the energy of that transition going from energy level 3 to energy level 2 is minus 3.049 times 10 to the minus 19. J stands for joules, which is the unit of energy that we use in science. And just to kind of, we haven't really talked about thermodynamics. I don't think you get into that until next semester. But if it is a situation where energy has given off, and I think you've learned that to be called exothermic. So anytime energy, any type of energy is given off, there's a negative sign in front of the value, meaning that energy is going lower. If energy were to be absorbed, so let's say that electrons started in a lower energy level and had to absorb energy to go to a higher energy level, then the value would be plus. We have learned that understanding the light that is given off by atoms tells us a lot about the structure of an atom. So I think before we get more into that, it's important to kind of do a quick refresher on light itself, the electromagnetic spectrum. And so just to remind you, the visible light, only tiny little fraction of the whole electromagnetic spectrum that we can actually see, is again a tiny little portion. Okay, the highest energy light is gamma rays, but X-rays are pretty darn high energy too, and one of the lower energies is radio waves, actually infrared, IR, which we perceive as heat. That is a form of light on the electromagnetic spectrum too. So let's go ahead and try to understand the behavior of light. It'll help us understand the studies that were done to determine the structure of an atom. So there are 3 important features that we need to understand with light. One is wavelength, and that is simply the distance between 2 identical points on a wave. So between crest and crest, or between trough and trough, that's wavelength. It is a distance. Okay, so it's typically meters, centimeters, nanometers. And then there is frequency. Frequency tells us how often a wave goes up and down, okay? And so frequency has units of 1/2. So how many cycles per second? That is frequency. You have probably heard that called hertz. So anytime you hear hertz, they're talking about the frequency of something. And there is an inverse relationship between wavelength and frequency. So let's look at that on the wavelength curve here. You can see that where we have long wavelengths or a large wavelength, the frequency is low. Okay, there aren't very many up and downs in a certain period of time. On the other end, if your wavelength is very short, that means your frequency is really high. And so something we'll go over in a few slides, but frequency and energy are directly related. Okay, so the higher the frequency, the higher the energy. And that I've always thought of that when I was learning as a student, that imagine me running along these waves. And if you had to run with this type of frequency, it would require a lot of energy, right? Whereas if you kind of had to run up and down like this, it would be lower energy. So more calculations. This is a PowerPoint with primarily based around calculations. So the speed of light, which we designate, let's see, I guess that's all we're going to do, which we designate with a little letter C, is a constant. It's fine for me to round it to 3 times 10 to the 8 meters per second. A lot of textbooks will say 2.998, but 3.0 is fine. So that is a constant, and it is a function of both wavelength and frequency. But since the speed of light is a constant, that means that the product of wavelength times frequency has to also be a constant. So you can see mathematically that wavelength and frequency are inversely related. As one goes up, the other one has to go down in order for the product of the two to be a constant. Now, as with any formulas in chemistry, you have to be able to rearrange them to solve for any of the variables. So I won't ever ask you to solve for speed of light. That's not a variable, it's a constant. But you need to be able to rearrange that to solve for frequency, and you need to be able to rearrange that to solve for wavelength. All right, we're going to do a couple practice calculations in a minute, but one more little piece of theory. So along came actually Einstein and started doing some work on black body radiation. And you don't have to know what a black body is, but basically it's typically a metal in our world, but it's something that effectively, if you apply heat to it, it's a total absorber, which means other things you apply heat to, like imagine applying heat to plastic. The plastic's not very absorbent of the heat, so a lot of the heat's going to escape into the surrounding atmosphere. But in a black body, they call it a perfect absorber and a perfect emitter, so you don't have to worry about the surroundings competing. But the bottom line is, and you've probably seen this, if you take a piece of metal and you put it in a fire, it's going to change colors. It's going to start out by glowing kind of red, and then maybe orange, and then yellow. And then as it gets very, very hot, white hot, you've heard that phrase, white hot, real distinct color changes. And so that study told scientists that, similar to what we had seen with Bohrs Model, was that light, remember that light coming off is always due to electron transitions. And so electron transitions have to be of a specific energy. It's not a continuous energy release. And so the abrupt change in colors from red, orange to yellow to blue to white represent also the energy levels that are undergoing transitions in that particular metal. And so that just confirmed what other scientists had proposed. And the scientist that actually came up with the formula to explain that is Max Planck, but Einstein did a lot of work with it too. And E is energy, right? So the energy of any type of light, okay? And H is Planck's constant, of course. They like to name them after themselves. I probably would too, I guess. And this crooked V is frequency of the light. And so this tells you that energy is directly proportional to frequency, just like we said on the last slide. And so if we take this equation, Planck's equation, and we combine it with the equation for the speed of light, what do I mean combine? Well, if I rearrange the equation for the speed of light to solve for frequency, so frequency is c over wavelength, and then I plug in for frequency into the energy equation, so take out the frequency and replace it with c over lambda, what I get is this. So this is the combined energy equation, which is a lot more handy. Because let's say that I asked you, let's say I gave you a wavelength, I'm just going to make one up, 500 nanometers of light. And I asked you, what's the energy of that light? Well, you would say, okay, let's see. If I want energy, I want this equation, right? But this equation doesn't have wavelength, and that's the only given information I have, okay? On the other hand, you could say, well, I could use this equation. Well, okay, you could plug in the wavelength, right? But you don't have frequency. So you could do a two-step calculation. You could first plug it into the speed of light equation and solve for frequency, and then go ahead and plug the frequency in a second calculation and calculate energy. This combined equation is a really handy one because it allows you to directly calculate energy if you're given wavelength. So let's do an example. What's the energy of a photon of light with a wavelength of 640 nanometers? Now, I told you before that scientists like to report light in nanometers because then they don't have to do all that scientific notation. But all of these equations take meters. So if you're given nanometers or any other prefix, centimeters, decimeters, anything, you have to convert it to meters before you plug it into that equation. So if you think you can do it yourself, I encourage you to turn off the video and do it yourself, okay? So here's my conversion. It's 1 times 10 to the minus 9 nanometers in 1 meter. And so if you go ahead and plug that in, and again, please plug this into your calculator and make sure that you're entering scientific notation correctly. The answer that you should get is 6.40 times 10 to the minus 7 meters. Now, if it's in lights and meters, it's almost always going to be 10 to the minus 7 exponent. If you did not get that exponent, if you got some crazy exponent, you are entering scientific notation into your calculator wrong. All right, so now we can go ahead and use the combined equation. So then energy is Planck's constant. And then the speed of light. And then the wavelength in meters. And again, please enter this into your calculator. I actually had a student one semester fail this first test because of entering scientific exponents incorrectly. So check it out right now. Make sure you know how to use your calculator. Alrighty, so I'm going to go ahead and enter that on the fly now. And you enter it, we'll see if we get the same thing. All right, and I get then the energy is 3.11 times 10 to the minus 19. Remember, the units are joules. And just kind of a heads up for you, this is a very common exponent when you're calculating energy of light waves, 10 to the minus 19. And that's it for this problem. We're almost done with the PowerPoint too. Alrighty, so as I said, Einstein was involved in coming up with that energy equation also. He actually verified it. He did something called the photoelectric effect, which standardized multiple choice exams like to ask you, what is the photoelectric effect? Well, the bottom line is you take some metal, copper, aluminum, whatever, and you shine light of a certain energy at it. And when the energy of the light reaches a high enough value so that it equals or exceeds the energy level of the electrons in the atom, then you can actually eject an electron from the surface of the metal. But again, because electrons are only in particular energy levels, remember I said electrons are quantized? Bohr proposed that. They can only exist in certain energy levels. And so if I draw the Bohr model again, there's the nucleus, and here are the energy levels. Okay, so let's say a particular metal had an electron in this outer energy level. It had some in the inner ones too, but we're going to ignore them for now. And this electron would not be ejected until enough energy, so it would be the energy that it's bound to the nucleus by or attracted to the nucleus by, it would not get injected until you shine a light on it with an energy equal to this binding energy. That just kind of verified the Bohr model as far as energy levels and also Planck's equation. Now, we have learned two separate equations. We have learned E equals h nu and C equals lambda nu. The frequency is that symbol is nu if you haven't heard that before. If you do not like algebra, if it's not your friend, and you can't rapidly rearrange these equations to solve for different things, like let's say I asked you to solve for frequency, or let's say I asked you here to solve for frequency, you may find these rearrangement triangles handy. So if you use one of those, just kind of remind you if you haven't used them before, whatever you're solving for, you cover up. So let's say on the top one that I ask you to solve for frequency. So you would put your finger over the frequency, and what's left is the equation you use. So if you're solving for frequency, okay, that means frequency is energy because E is on top over Planck's constant. Now, this is weird. Okay, looking at the one for the speed of light. If you are solving for frequency here, okay, cover up frequency and what's left. It tells you that frequency is the speed of light divided by wavelength. So those are just there if they're handy, and that is it finally for this PowerPoint.